This third video on hypothesis testing basics focuses on p-values and decision-making. In addition to significance level, the p-value is one of the most common statistical terms reported in the scientific literature. Let's return to the example of the effect of fluoride on remineralization of primary root caries lesions. Bazin et al. Found better results for Prevident after 3 months, with approximately 38% of the subjects using Prevident, compared to 11% of those using Winterfresh gel, having one or more primary root caries lesions that had hardened. P equals 0.005. What does this P equals 0.005 mean? They found similar results after 6 months. P equals 0.002. Again, what is the meaning of P equals 0.002? The researchers concluded that the dentifrice containing 5,000 parts per million fluoride was significantly better at remineralization of primary root caries lesions than the one containing 1,100 parts per million fluoride. These differences were significant, so the numbers at the top of this slide indicate significance somehow. Let's find out what these numbers mean. Now back to our scenario where a researcher is trying to replicate the Bazin et al. Study. This is the distribution of all the possible results when the null hypothesis is true. The arrow indicates that the researcher expects results to be in the upper tail, reflecting better results for Prevident. The researcher has already set her significance level, which is never set lower than 0.01, 1%, and never higher than 0.10, 10%, with the most common being 0.05, or 5%. In this case, the researcher set her significance level at the conventional value of 0.05, or 5%. The p-value, or p, is defined as the probability of getting results like those the researcher got when the null hypothesis is true. Suppose that the researcher finds a mean difference at this point along the distribution. The difference is above 0, which indicates that the sample mean for Prevident was higher than for Winterfresh gel. The p-value for her test is approximately 0.15. By convention, a p-value represents the likelihood of getting a result at least as extreme as these results, so it will always be the area from the test result through the tail of the distribution. Would the researcher reject the null hypothesis on the basis of these results? She set her maximum risk of rejecting a true null hypothesis, that is, the significance level, at 0.05. This created a decision rule. Any result that can happen less than 5% of the time by chance will be taken as evidence against the null hypothesis. A p-value of 0.15 means that there's a 15% chance of getting such results when the null hypothesis is true. 15% is a level of risk beyond the 5% maximum, so the researcher would not reject the null hypothesis. These results do not provide evidence against the null hypothesis. Another way to say this is that the results are not statistically significant. Looking at where the test result falls on the distribution, we can also see that it is not in the rejection region, a further indication that the researcher would not reject the null hypothesis. The researcher's conclusion is that the results do not support the research hypothesis. There is no evidence of better remineralization for higher fluoride concentrations. Note that the reason the area for the p-value goes through the upper tail and not the lower tail is that the research hypothesis states that Prevident will provide better results. That is, she is looking for differences only in the upper tail. This means that even if she obtained a mean difference down in this tail, she would not reject the null hypothesis, because the p-value is the area from the test result through the upper tail. The question is, how likely is it to get a mean difference at least as large as this when the null hypothesis is true? And in this case, it is quite likely. We can also see that the researcher's result does not fall in the rejection region. The p-value exceeds the significance level, so the null hypothesis is not rejected. This brings up an important point about one-tailed tests. They should be used judiciously. A researcher should not do a directional test unless she is quite confident that any difference will be in that direction. In this last example, the researcher was obviously looking in the wrong tail. However, in this area of research, such a result is unlikely. The researcher based her hypothesis on prior research, which suggested that higher fluoride concentrations will result in more remineralization, and not less. Let's look at one more possible outcome. Suppose that the researcher finds a mean difference at this point along the distribution. The p-value for her test is approximately 0.03, the area from the mean difference through the upper tail. Would the researcher reject the null hypothesis on the basis of these results? Yes. A p-value of 0.03 means that there's only a 3% chance of getting such results when the null hypothesis is true. 3% is a level of risk below the 5% maximum. The p-value is less than alpha, so the researcher rejects the null hypothesis. This means that the results are statistically significant. Also note that the mean difference falls in the rejection region. The evidence supports the research hypothesis. The researcher rejects the null hypothesis and concludes that higher fluoride results in better remineralization of root caries than the standard concentration. Returning now to the Bazin et al. Results, the researchers used a significance level of 0.05 and found statistically significant differences in remineralization at both 3 and 6 months. This means that they rejected the null hypothesis of no difference at both time points. The p-value of 0.005 for the 3-month results indicates that differences at least as large as those the researchers found could occur by chance, that is, when there is no real difference in remineralization, only 5 out of every 1,000 times if the study were repeated. At 6 months, such results could occur by chance only 2 out of every 1,000 times. Based on these small p-values and a significance level of 0.05, the researchers concluded that there were real differences between the two fluoride concentrations. To summarize the process of hypothesis testing, the researcher starts by stating the research and null hypotheses. She then draws a model that represents all the possible results she can get when the null hypothesis is true. Next, she sets the significance level, alpha. This is the researcher's maximum tolerance for rejecting a true null hypothesis, and is usually set at 0.05. She then collects her data and analyzes the results. The test statistic she produces also has a p-value associated with it. This p-value represents the likelihood of getting similar results, that is, at least as extreme, when there is no real difference. She then makes a decision based on her results and the decision rule she established by setting the significance level. If the p-value is greater than the significance level, she does not reject the null hypothesis and concludes that the data do not provide evidence of a difference or effect. If the p-value is less than the significance level, she rejects the null hypothesis and concludes that the data do provide evidence of a difference. The significance level and p-value are probabilities under the distribution that represents the null hypothesis. The difference is that the significance level is set in advance by the researcher, whereas the p-value is determined strictly by the result of the statistical test and is therefore directly tied to the data. The final video in this series, coming next week, will focus on statistical power, confidence intervals, and dealing with uncertainty.